All right, silly people, here's the situation. Shankar wants us to calculate the total cross section for the Yukawa potential. Um, and he already happened to have calculated the differential cross section of it in the Born approximation. So all we really have to do is take an integral. And what an integral it is. Let me just say that. So I'm just going to collect these terms out here. And then also do the phi integral. There's no phi components in this, so you just get 2 pi from that. But then the theta integral is the interesting one. And I'm going to make a substitution, or it's not really a substitution, it's just making use of a trig identity where sine squared of x is equal to 1 minus cosine 2x over 2, right? Whatever. It's over 2. Um, and so in this denominator here, we just get mu naught squared plus 2k squared minus 2k squared cosine just theta right there. So that's pretty awesome. Now I'm going to make a substitution where I'm going to define a variable x as being everything in the denominator. So that junk there, and then the derivative of that with respect to cosine theta is just minus 2k squared. And so flipping the sign, bringing the 2 out of the square, we get minus 8 pi times this mu g over h bar squared. This is what we're doing here now. We have 1 over 2k squared from changing over the integration variable, and then we have minus 1, not minus 1 actually. If we plug 1 for cosine theta into the definition of x, we just get mu naught squared. If you plug in minus 1, you get mu naught squared plus 4k squared. But then you just have the integral of 1 over x squared dx. And that's not too terrible. Simplifying a bit, look at a minus 4 pi here. We can move the k into the square. I always forget to actually write the square on the square. And then this integral is just minus 1 over x. And then the integration bounds. And so we'll flip the sign again, and then we'll have mu g over h bar squared k all squared, and then we have to deal with this interesting no, it's 1 over mu naught squared plus 1 over mu naught squared plus 4k squared, and actually there's a minus sign. Okay. So without changing around the factors outside just yet, I'm going to combine these under the same denominator, so we'll have mu naught squared plus 4k squared minus mu naught squared all over mu naught squared times mu naught squared plus 4k squared. And then these will cancel out, and that's fun. We can factor out that 4 to get 16 pi, and then the k's will cancel out, so we have just mu g over h bar squared all squared. We'll have an additional factor of 1 over mu naught squared, but then it's divided by this mu naught squared plus 4k squared. And this is when I'm going to apply the definition of mu naught as being 1 over r naught, and change the notation over to 16 pi r naught squared mu g over h bar squared. And then this is going to be 1 over r naught all squared plus 4k squared. And we'll multiply it by another factor of r naught squared to get the form that Shankar got with a r naught in here. And I forgot to square it again. It's 1 plus 4k squared r naught squared. And yeah, that's what Shankar got. If we compare this to the geometric cross section, now this is the part of the problem where I'm not really as sure, but I'm pretty sure the geometric cross section is just half the surface area of the sphere that it's scattering off of, quote unquote. So it's like that. If we happen to be in the limit of large k, so particle moving kind of fast, so I'm going to say for k much larger than 1, we kind of have that term. We have 4 pi r naught squared, just treating this as small or really large. We have this r naught squared, no, all over h bar squared, all squared, and then over k squared r naught squared, and then the r naught here will cancel out the r naught there, and so we just get 4 pi times, let's do 4 pi r naught squared times mu g over h bar squared k all squared. And so we recover like the geometric term, but with this funky little quantum correction, which isn't like too ridiculous, I think.